Good morning, everybody. We're going to continue on with 15.3. And so we're going to talk about our buffering capacity here. I think in the last podcast, we talked about that a buffer is something that resists change, and our ideal ratio between the acid and the conjugate base is that if that ratio is 1. Also, we're going to talk a little bit about that if our pH is equal to our pKa, then it also is going to be a good buffering situation. And you can see here that I have the different scenarios that if our pH is less than our pKa, then we have more weak acid in solution, or vice versa with the base. So we're going to take a look at how this affects our titration curves, and hopefully at some point we'll get this lab completed. But the titration is used to determine the amount of acid or base using a known concentration. So in this curve that I have right here, it is a strong acid plus a strong base. And we can see that we have our titration curve here, and if we look at, we have a really low pH, so that should recognize to you that that is a very strong acid. And this over here that you can't see says midpoint. So the midpoint of this line before it gets up to this point of the curve, so middle, right? So that's our midpoint, is equal to our pH is equal to our pKa. So then that means it's a really good buffering situation. So if you think about this really strong acid, we keep adding a base, it's buffering, it's absorbing it, like our blood in our urine, okay? And then all of a sudden, the pH is going to change. It's going to get to our equivalence point, as I have over here, where the moles of the acid equals the moles of the base, and or the hydrogen ion concentration equals the hydroxide ion concentration. So this side of my curve is going to be my acids, this side of my curve is going to be my base. And you can see the flip of that is true, that if I start with a strong base, you can see my pH is way up here. Again, it's buffering, gets to the midpoint, pH equals pKa, and then the pH is going to greatly drop, and again, reach our equivalence point. Something else that we need to remember is that when we have a strong acid plus a strong base, that I have my strong acid of nitric acid plus sodium hydroxide, that I get water and a salt. Well, this is a spectator, right? And we have our water. So the nitrate is a spectator, our sodium is a spectator. So really all I have is the hydrogen ion, the OH for the base ion making water. And that's what I'm going to be showing you here with these strong acid base titrations. Now, because I do not have any NaOH added here in this first one, I have 50 milliliters of 0.2 molar nitric acid, okay? And when I add some NaOH, it's going to be of a 0.1 concentration. Well, because I haven't added any NaOH, I need to recognize, oh, this is a strong acid, completely dissociates, so the concentration of these are all the same because I have a strong acid. And so then I can just go ahead and take the negative log of my hydrogen ion concentration, I get the pH. Now, is it buffering? So this is where we're trying to make that titration curve that I just showed up above. So again, I want to do this in moles or millimoles, as you'll see here, so I'm just not canceling out the milli here, is I have a certain amount of my acid, 0.2. I added 50 milliliters of it, which is going to be our constant all the way through this example. And then I'm adding 10 milliliters of 0.1 NaOH. So I have the concentration times the volume gives me moles or millimoles. It's just easier to use these bigger numbers here, so I'm not going to move the decimal 3 to the left. We're just going to keep it like this because it's easier to look at. As you'll notice over here, the milli will cancel out anyway. So concentration times volume gives me moles or millimoles. Concentration times volume gives me millimoles. I can see that all of this is going to be used up. It's a limiting reactant, and so this is also going to decrease by 1. I don't have to worry about anything on the product side because I don't concern with water anyway. So my hydrogen ion concentration is going to be the number of moles over the total volume. So I had 9 millimoles that's left. The total volume was the 50 right here, plus the 10 for the base. So my hydrogen ion concentration is 0.15. Take the negative log of that, and there's my pH. So if I go ahead and start graphing that, I made this little graph on the next page, and I put in spot A and B over here. We are still buffering. It's not moving a whole lot. I continue with the same example all the way through. I still have those 10 millimoles I started because I'm always going to be using 50 milliliters, and then changing the amount of base that I'm adding. And so you can see in part C, the pH is starting to go up. I am now at the equivalence point for part D. Make sure you're reading through all of this and looking at the graph and understanding what I'm doing. And then on part E, I'm just doing the same exact thing, but now my base is going to be what is left over. And so I have to do a little extra work to get to my pH. Keep in mind that you are finding your hydroxide ion concentration here. So you actually found your POH, so I have to subtract that from 14. And now I'm on the other side of my titration curve. So that didn't happen until I added 150 milliliters of my base. And then F is exactly the same, and you can see that I'm on the other side. So all of this are these titrations. We were doing a strong acid and a strong base, which is this line down here. All right, it takes a lot longer. Needs a lot more things to added to it, a lot more ions, until I get here. You can see that my range of straight up and down of my pH is much wider when I have a strong acid and a strong base. But I can still have it happen at the same pH. Here's my weak acid. It just is a little bit higher up. And then that range where they change and flip is a lot shorter. Okay, let's see if there's anything else. No, that is it for that section. All right, you guys have an awesome day.